As we're continuing through rotational stuff, we're going to look at our next concept, which is torque. Torque is the rotational equivalent of force. Torque is the Greek letter tau, and it is equivalent to our force. These are parallels. We've got x and y to theta, v to omega, a to alpha, mass to moment of inertia, kinetic energy, translational or linear, and this is Ke rotational, and then force and torque. So torque, just like force causes an acceleration, torque causes an angular acceleration. It changes the spinning motion of an object. And it's exactly like force. Force equals F equals ma. If we plug in our rotational equivalents, torque is I alpha. Moment of inertia times angular acceleration. All right. Moment of inertia, I, has units of, it's mr squared. It has units of kilograms times meters squared. Alpha has units of radians per second squared, but radians dimensionless. So our torque has units of kilogram meters squared per second squared, which is Newton meters. And it might be strange because Newton meters is also the unit of work. The difference is that torque is a vector. It has a direction, clockwise or counterclockwise. And while work or energy don't have a direction, they are scalar quantities. Right? And just like Newton's second law, this is the net torque is equal to I alpha. Okay, at this point it's useful to talk about something called the right-hand rule. And that is used often to define the direction of a torque. So torques cause an object to rotate. So let's say you've got an object and it's rotating around this way. You're opening a door or something like that. Okay. This is counterclockwise. It's against the rotation of the clock. But the right-hand rule says we can give this direction. It's just kind of a standard for a way to convey this direction. And this direction is given by what your right hand does. So we're moving this way. So you point your finger, you curl your hand along the path that this object is traveling, and then wherever your thumb is pointing is the direction of the torque. So I curl my hand around here, which tells us that the torque is going this way. So if our torque is counterclockwise, which this is, we say it is coming out of the page, because that is the direction my thumb is pointing when I curl my fingers that way. If torque is clockwise, that would be the other direction. I have to turn my hand over to curl my fingers that way, which means that my thumb is pointing downward, is pointing into the page. So that's going to be how we determine the direction of a torque. It's by using this right-hand rule. Okay. So torque is net torque is the moment of inertia times acceleration. Torque is also related to force, just like our other quantities. It's a force times a distance. It's actually a cross product. if you know vector operations. I think you do that in calculus. So if you've done that, that might be meaningful to you. For those of you who don't know that, the cross product, the magnitude of the torque is the magnitude of the force times the radius times the sine of theta, where theta is the angle between the force and what's called the lever arm. Okay, that sounds weird, but basically, like, say you've got a door here, and the hinge is here. This hinge is your pivot point, and you apply a force to the door, like, say, like this. Okay, this is your angle. This is the angle between the force. The lever arm is just this imaginary line from the pivot point out to the point where the force is being applied. Okay, usually it's right along the object. Yeah, and you kind of already know this. You know that to push on a door, you want to push perpendicular, like you want to apply a force perpendicular to the door. And if you apply a force perpendicular to the door, it's easiest to open the door, right? Well, that's because, you know, this sine theta becomes sine 90. That's the angle between the force and the door, and sine 90 is 1. So that's giving you the maximum amount of torque for the force you're applying. Likewise, if you push on the end of the door, push it toward the hinge, you know you're not going to get anywhere with that, and that's because your angle is 0. Sine 0 is 0, and so you're applying 0 torque. Okay. Another something kind of odd about torque is that, and its relationship to force can be demonstrated here. So we've got a pivot point in the middle of an object. This is some rotating object that's anchored in the middle. If you apply a force here and a force here, what's going on? These two forces are in opposite directions. But this force, pushing upward, would cause the object to rotate this way, which means this force is causing a torque out of the page. This force is pushing this way, which is also causing the object to rotate the same direction. So this torque, the torque from this guy, is also out of the page. So with forces in the opposite direction, our net force is 0, but our net torque is not 0. So that's kind of a strange thing that, you know, doesn't seem very intuitive. Likewise, if we have forces in the same direction, here our net force is not 0 because we have two upward forces, but this one causes a torque going this way, this one causes a torque going this way. Those are in opposite directions. The one is out of the page and the other is into the page. The net force is not 0, but the net torque is 0. So both of these can happen, even though torque is Fr, is force times radius. This is for an individual torque, or like the net torque would be the net. No, this is for an individual torque. Each individual torque is Fr sine theta, but multiple torques, you can't just add up the net force and plug it in here, because a force in one direction could cause a torque in the opposite direction of another force going in that same direction, depending on where your pivot is, right? So that's something to keep in mind. Let's just do a quick example here. Let's say we've got a teeter-totter initially at rest, and these two people sit down on either side at the same time. And I want to know, and let's say this teeter-totter has a mass of, I don't know, 220, that's too much. Say it has a mass of 93 kilograms. Okay. And I want to know the angular acceleration of the teeter-totter. Okay, well, we know net torque equals I alpha. We have if I call this person A, call this person B, we have two torques, torque from person A and torque from person B. This teeter-totter can be considered a uniform rod. This pivot point is in the middle, so we can call that moment of inertia the 1/12 ml squared alpha. Okay. So person A is applying a downward force, the force of gravity. It's perpendicular to the teeter-totter, so our theta is 90, so the sine 90 becomes 1. So you just have force times radius. So we have force 85 times 9.8 times the distance from the pivot point, 2.5. And that is applying a force in the counterclockwise, or applying a torque in the counterclockwise direction. While this one is also applying a downward force of mass times gravity times distance, 2.5, but this one is applying a torque in the clockwise direction. And we're just going to, in order to make things easier, we're just going to say that clockwise is going to, or counterclockwise is going to be positive. And that's easiest to remember because it makes your thumb point up or out of the page. So counterclockwise is positive and clockwise is negative. Remember, signs are arbitrary, so that's the standard that we'll use, but it's not like the end-all be-all of everything. And that's equal to 1/12 times the mass of the teeter-totter times the length of the teeter-totter, which is going to be 5 meters if it's 2.5 to the end, times alpha, 5 squared, times alpha. So you can see the initial angular acceleration is about 2.529 whatever radians per second squared. Most of your problems will be simpler applications even than that, but some could get more complex. But the principle is here, so you figure out the torque from each object, apply the appropriate sign based on what direction it's going, and then you set that equal to I alpha.